Good afternoon, everyone. My name is Scott Lee. So I lead the team in the Windows OS that owns the lower part of the Windows storage stack. So in today's session, I'm going to share with you about storage multi-queue, which is a new lower storage stack that we're building in Windows. So within Microsoft, we call this project the Native NVMe Technology Project. So this is a redesign of the Windows lower storage stack to optimize for high performance multi-queue storage hardware using NVMe technology concepts and features. So internally, we refer to this effort as storage multi-queue or StoreMQ for short. So as part of this project, we are extending the Windows StorePort storage driver model to support both the existing, I'm going to call SCSI-based mini ports that we have today, with support for a new class of StorePort mini ports that we call StoreMQ. So this new architecture provides significant improvements in terms of CPU usage, performance, and multi-device performance scalability compared with our current existing stack. So on this slide here, I have a picture of the Windows storage stack. So on your, I'm not going to use right or left, but the pieces that are shown in gray, this is the existing Windows storage stack. So at the top, we have the file systems. Below it, we have a volume. Below the volume, we have partitions. And below partitions, we have a disk layer. And then we have what I term an adapter there before it interacts with the storage hardware. So the pieces in the slide that are shown in blue are part of what I term our new stack, our StoreMQ stack. So as part of this new stack, we are introducing a new disk layer driver, and we are extending the StorePort model to have a new workflow to be able to work in the StoreMQ stack that will be using of NVMe concepts and definitions. And that will interact with new StorePort mini ports that we term as StoreMQ mini ports, which will work in this new stack. So within this new model, StorePort will be creating queue pairs that can be used directly by hardware. So as an example, for the Microsoft PCIe NVMe driver, StoreNVMe, it will directly use the queues that are created within StorePort. With the StoreMQ effort, we went about with several design goals as we work on architecting and implementing this. And our number one goal was to replace the existing SCSI-based architecture with NVMe commands, concepts, and data structures. So rather than going out and looking for SCSI nuns, we will now enumerate for NVMe namespaces. In terms of the queues that use within StorePort, StorePort will have native support for both submission and completion queue pairs, and we will be using the NVMe-based definitions for it. Within the new stack, there will no longer be a separate queue for nuns and adapters. In this new model, StorePort is going to be the entity that will be doing the queue allocation and management. And StorePort will share information about these submission and completion queue pairs with the miniport. So our goal is to minimize bottlenecks within our implementation. So our goal is try to make the workflow as lockless as possible to enable better performance and scalability. Within this new model, we are adding a logical NVMe-based controller abstraction into it. So we will allow a miniport to dynamically add or remove NVMe controllers. This is the opt-in model. So the current store port mini ports that are in use today will continue to work. But we wanted to build support for the ability for folks to develop a new type of store port mini port that could plug into this new stack. So on this slide here, I have a diagram of what is the comparison in the I/O path between what we have currently today in Windows versus this new stack that we're building. So again, all of the pictures in gray are showing what does it look like today within the current stack. So for reads and write, the request will come down to the disk layer. And in the disk layer, we will basically translate that read and write to effectively a SCSI op read or write. And then what actually makes it out to the mini port is a SCSI command. And then if the mini port is supporting a non-SCSI hardware, then it'll do a translation from SCSI to whatever the command protocol is. So on this slide here, I'm showing the Microsoft SATA driver. So our SATA driver, store HCI, will take SCSI and convert it to ATA before sending it out to the hardware. Now in the new stack in blue, for reads and write, what will be happening now is the reads and write will flow directly into store port, where the store MQ code within store port will then take that read and write and then generate the equivalent NVMe read or write command, and then submit that command into a submission queue. And for the Microsoft NVMe driver, once it submits it to the submission queue, it is going directly to the hardware. And within this model, we do have the ability to support non-NVMe hardware also. So we're working with various industry partners out there on building store MQ mini ports to support storage HBA. So these are like RAID controllers. Where now, because if you look at the RAID controllers today, they have a lot of, they're all multi-Q pair based, and then they have a lot of capability in terms of the performance that they can provide. And the other thing to note on this slide is it shows NVMe over Fabric mini ports. So we are working on building NVMe over Fabric initiators within Windows that will also plug into our new Store MQ stack. On this slide here, I am showing the object hierarchy within the Store MQ model. So at the very top, we have the NVMe adapter. As part of the NVMe, the way you should view an NVMe adapter is this is a hardware device. So from a hardware device, it has the ability to support one or more NVMe controllers. And then as part of the NVMe controller, it has the ability to support one or more namespaces. So within the Store MQ model, a namespace will be exposed to the rest of the system as a disk or a physical disk. And from the perspective of the rest of the system, they will be able to see the NVMe adapter and then all the disks that are exposed. In this new Store MQ model, there will be need for us to exchange information between store port and the new Store MQ mini port. And the way we've chosen to do that information exchange is to adopt the NVMe property concept. So from a mini port perspective, mini port will expose new callbacks that allow store port to query or to set properties. So in terms of the properties that will be supported within Store MQ, we have three categories of property. We have the properties that are defined in the NVMe spec, such as the capability. We have also things that are defined in the NVMe spec that we term formulaic offsets. So these are things like doorbells. And then we have additional need to pass information that's not defined in NVMe, but where we classify those as store MQ properties. So some examples of these are, what's the base address of a particular queue? Or what is the mapping between the logical processor and the submission queue? And on the slide here, I've shown what is the callback signature of the set and query properties. I mentioned previously that within the store MQ model, store port is the one that's going to be managing and creating the queues that will be used. So store port will allocate the memory for all of the submission and completion queue pairs. When those queues are created, store port will share both the physical and the virtual addresses of those queues with the miniport. And we will provide the ability for miniport to customize the affinity for things like what's the logical processor to submission queue mapping, or the submission queue to the completion queue mapping, or the completion queue to the interrupt vector mapping. So if a miniport wants to customize that affinity, it'll provide callbacks that store port could call into to pass that information into store port where it will apply it. If the miniport decides that it doesn't want to customize that within the store MQ logic, we will have our own algorithms for determining the affinities. And once the affinities are finalized, store port will share that information with the miniport through the set property callback. As request comes in, store port will be the one that basically generates the NVMe command, assigns the slot, the queue slot, and also the queue ID that's used. If a particular submission queue is full, store port will buffer that request until free slots are available. So from a store port perspective, store port will be responsible for the submission queue tail and the completion head of the submission and completion queues. And then it will send a logical doorbell ring to the miniport through the set property callback. And from a miniport perspective, it will act as a controller where it will modify the submission queue head and completion queue tail. And then those will be implicitly passed to store port through the completion queue entries that the miniport will generate in terms of that shared completion queue. On the next slide here, I have a picture of what the submission queue and completion queue layout look like within the store MQ model. So if you look at what's shown here, it is very similar to what's defined in the NVMe spec, except for we've added some addition on the submission queue side, where there is some additional context that we need to have associated with each of the command that the miniport may want. So we built mechanism to be able to provide those additional contexts.
Could I ask a question? I want to make sure I heard you correctly on the previous slide.
Yep.
Did you say that the store port chooses the queue ID that the command will be sent on?
Yes.
Okay.
So the question is, no, within the store MQ model, does store port choose what submission queue a command will be put in? And the answer is yes. So in the next few slides, I'm going to go through the workflow of what a store MQ, what a store MQ miniport will do. So the first workflow that I will cover is the initialization workflow. So like all typical store port miniports, the first function that's called is driver entry. And for a store MQ miniport, it will also call store port initialize when the driver entry is called. Except for in the new model, it will have to pass in an additional feature flag, which is a store feature store MQ miniport. So this gives StorePort the ability to know I am interacting with a miniport that can support store MQ. And then for the rest of the workflow, this is the very typical workflow that you will see in Windows as part of the Windows plug-and-play process. So when new instances of devices are discovered that uses a particular driver, the add device callback will be invoked. And when that is done, the store MQ will create a private adapter object. And then later on, when PMP is ready to start the device, now you will see a PMP MN start device. And this is where we will start to initialize the hardware. So like the current model, the HW find adapter callback from the miniport is invoked. After this function returns, there is a new callback that StorePort will call into StoreMQ miniport, which is a new adapter control, where it's going to query the miniport for additional callbacks that are specific to the StoreMQ model. So this is what the NVMe adapter query StoreMQ interface is all about. Afterwards, StorePort will call the HW passive initialize function. So this is the same callback that is available today for StorePort miniports. And if you are a StoreMQ miniport, within this callback, you will add controllers by calling StorePort StoreMQ add controller. So from a miniport perspective, you have the ability to add one or more controllers. And then once the passive initialize routine returns, the StoreMQ code within StorePort will start to initialize the controllers that have been reported to it. So for each of the controllers that are presented to it, it'll go through a init sequence. And for the init sequence, if you are familiar with the NVMe spec, I think a lot of this workflow that I will talk through will look very familiar to you, because we are pretty much doing whatever is specified within the NVMe spec with some additions. So the first thing that will be done as part of initializing a controller is to get information about what's the admin queue size. So this will be done through query and set property calls to retrieve information about the admin queue size. The StoreMQ code will also query the miniport for information about whether the supported IOQ devs, what's the doorbell stride, what is the various controller timeout values. And then it'll create the admin queue. So once the admin queue is created, it will share information about both the physical and virtual address with the miniport. And then afterwards, we will go through and start to initialize the controller by basically setting the cc.en through a set property call. And then we'll wait for the ready bit to be set in CSTS. And then after the admin queue has been created, after we know that it's been started, the controller has been started, we'll start to issue a bunch of admin commands to basically set up the controller. So among the things that will be done are to get information about the controller through the identify controller command. We will also discover what are the active namespaces that are available on that controller. And that is, again, through the identify commands for looking for active namespaces, and also to query for Are there any like namespace the identify CNS specific namespace command? And then the next step is to determine what are the appropriate number of IO queues to set up. So this will be again done through admin commands from NVMe through the number of queues feature. So after information about the number of IO queues that are available for both submission and completion queues, then the STORE-MQ logic will work on determining what is the number of queues for both submission and completion it will create. Prior to creating these, it will first query the miniport to see, do you have specific affinities that you want to be used? And that is done through various query property calls. So once all that information is gathered, the STORE-MQ code will then go and start creating IO queues. So the first thing we do is we do create the completion queues first, and then we create the submission queues. And after the IO queues are created, it will then issue a bunch of log pages to determine what are the supported logs, supported commands, supported features that the particular controller supports. Next, I'm going to go through the workflow for what the command submission would look like within the STORE-MQ model. So as request comes in, the STORE-MQ code within StorePort will generate the corresponding NVMe command. It will select the appropriate submission queue, and it will allocate the slot to use and the command ID to use associated with that command, and then copy that command to the submission queue. And then it will call into the miniport to basically ring the tail doorbell. So from the miniport perspective, if the miniport has to do additional work to program that command to hardware, that the miniport can do that when the doorbell is rang, or it could do it in what's called a DPC on Windows, which is a deferred procedure call, where what the miniport could do is in a deferred procedure call, it could take all of the SQE, the submission queue entries that have been copied to a particular submission queue, and actually dispatch it to the hardware. So if we're talking about a non-NVMe hardware, it will do whatever is needed to generate the equivalent command. On the completion side, so I'm going through the workflow for an interrupt-based completion. So when the command has completed, the device will generate an interrupt. As part of the typical StorePort model, StorePort will call into a miniport callback that's basically the ISR. It's the interrupt servicing routine. So within the miniport's interrupt service routine, it will look at this hardware to look for, do I have a completed request or not? And if the miniport has detected any type of completed request, it will then call back into STORE-MQ to ask it to please schedule a deferred procedural call on the command's initiating processor. So on the Windows side, we try to service a command on the same processor where the command originated from. We think this gives the best performance. So that's the default behavior that we use within Windows. Now, when the deferred procedure call run is executed, if the miniport supplies a callback, the STORE-MQ code will call into the miniport, and that'll give the miniport the opportunity to look at the hardware queues and then add or generate the completion queue entries to put into the shared completion queue between the miniport and store MQ. And when that callback returns, store MQ will go through the completion queue and then start processing all of the completion queue entries and then completing those requests back up the stack. And when it's done with that, it will ring the completion head doorbell to the miniport so that if the miniport needs to do any adjustments on the hardware, it has an opportunity to do so. So within the store MQ model, we are also supporting a new concept that is not supported in the current Windows Store stack. And this is the concept of a child adapter. So when we went and talked with various partners, we gotten feedback from a number of them around the desire to have a single store port miniport driver that can participate in both the current SCSI-based stack and the new store MQ or NVMe-based stack. So to support this, we are adding this new concept of a child adapter, where the child adapter has a separate HW initialization data so that we could have a completely independent configuration that could live side by side. So to simplify things, we are constraining the child adapter support with some limitations. So we are only supporting a single level of a parent and child adapter with only one child adapter. So I have a slide on the next one that hopefully makes it this a little bit clearer. So with this limitation, a parent adapter can only have one child adapter. And a child adapter cannot have another child adapter. But if you have multiple parent adapters, each parent adapter can have its own child adapter. So within this model, our store port will be managing the child adapter's function device object. So this is a concept that's common to the Windows driver model, where the FDO or the function device object is providing just the typical capabilities of a device. And then you also have a physical device object, which is more around on the bus level, what are the more bus level attributes of a device. So on the slide here, I have a picture that hopefully shows this in a way that's easier to understand. So first here, this is what we typically have today. So we have the adapter FDO that has an associated adapter PDO. You have a PDO to FDO one-to-one, and then as part of the FDO, it can have one or more child. So in this case, I am modeling, this is a SCSI-based stack where an adapter can have like multiple logical units. So with this new child adapter concept, what we're enabling is the ability for a SCSI-based parent adapter to also expose a child adapter where the child adapter will be using not the SCSI stack, but the new store MQ NVMe-based stack. And the restriction previously where I mentioned that we're restricting it to only a single level is basically what's shown here. We have a single level relationship between the parent and the child. And for this child adapter stack, you cannot have another child adapter. So In closing, in terms of the current status of where we're at with this new stack and this new model, this is currently in preview and available to NDA partners on Microsoft. We are currently working with both internal and external partners on creating StoreMQ-based miniports. This will require Collaborate access. So Collaborate is a tool that we use at Microsoft to share collaterals that are related with Windows, including preview Windows builds with our partners. Our plan is to release the StoreMQ model to sim ship with the availability of a StoreMQ miniport. So if you have interest in developing a StoreMQ miniport, please come talk with me. We have limits in terms of the number of partners that we could support prior to release. So no, there may be opportunity for like 1 or 2 more partners that we could support. So if you do have interest, please come and talk with me. And that is my talk today about StoreMQ. Are there questions? Okay.
If I understood you correctly, the number of IO queues that are created are determined by the affinities that have been...
No, that's not correct. So the number of IO queues that are created is very similar to a typical NVMe device. So basically, in a typical NVMe device, the driver will call into the device with like the number of queues feature, and then the device returns to the driver, here's the number of submission completion queues that you can allocate.
That the drive supports?
That the drive supports, yes. Right. Now similarly in the StoreMQ model, it works the same. So StoreMQ will call into the miniport to say, give me the number of queues that that you can support. And then the miniport returns that information back to StoreMQ.
And then how many actual queues does it decide to create?
Well, I think that's going to vary, but obviously the max will be based upon the response of the number of queues feature. Okay, so the question is, could we oversubscribe? It is a possibility. So if the response for number of queues comes back with less queues than I have CPUs, then there will be sharing. There's no way around it. Yep.
So continuing with the same discussion, so in store queue, right, the number of queues is per core or per socket base. For instance, if we have a NUMA model, right, and there are, like, for instance, 4 sockets, and each socket has a number of cores. So is it my understanding correct that you can already define the minimum number, maximum number of cores, queues based on the NUMA model itself?
So, okay, the question is for queues, how are queues associated with things like NUMA nodes or core? I think the answer depends upon the policy that's used. So within Windows itself, our preference is, if possible, we would like to give each core its own dedicated queue pair. But the other thing to note, and I want to, this is more forward-looking. So as I look forward to the future, there will be cases where we, from the OS side, Windows OS side, would like more queues than the number of cores. Because in the future, I could see use cases where we're going to dedicate certain queue pairs for certain usages, beyond just the typical mapping that's used today for core to submission completion queue pairs. Okay?
Will you
support change from the interrupt model to like pooling model, like Linux has?
Okay, so the question is for I/O servicing. Will we support other models other than interrupt-based? So the answer is yes. The two other models that I think we do have it implemented. The two other models that we have implemented, we do have support for a full polling-based model. And then we also have another model that we call hybrid, where we use a mix of interrupt and polling. Yep.
Yeah, and when you were mentioning about the parent-child relationship,
Yep.
and is that, well, SCSI devices could use the star and queue, why would I do that and not stick with the regular support?
Okay, so I think it really, I feel like, okay, the question is, if I have a SCSI-based device, why would I want to use the new store MQ-based stack versus sticking with the existing SCSI stack? And the answer to that is, I mean, obviously you don't have to. But one of the reasons for why a SCSI-based device may want to consider switching to the new store MQ stack is if your SCSI-based device, from a hardware architecture perspective, is submission completion queue based. In that case, I feel like you would want to consider switching to the new store MQ stack because the performance ceiling on that stack is a lot higher than our current SCSI-based stack. Okay.
Going back to the cores, we have run into situations where we have more cores than we have interrupts. Is there any provision for pairing up, like pairing cores, like hyperthreading or something like that?
Right. So, okay, the question is, there's going to be cases where on this system there are more cores available than interrupts, and what's done in those cases?
How do you pair the cores?
Right. How do you pair the cores? So the answer to that question is yes, that can happen. So our default logic is the number of if we're in modes that are using interrupts. So the number of completion queues that are created is gated by the interrupts that are available. Okay, so we want to give each completion queue its own MSI expector. So in cases like that, you can run into situations where, say, if you have more submission queues than completion queues, then you will see multiple submission queues sharing a completion queue.
But do you have logic to pair the cores intelligently that are using the same submission queue?
Right. So the question is, do we have logic to pair the cores correctly in terms of cores that are sharing either submission queues or completion queues?
Not all cores are created equal.
Yes.
Some cores have a
Okay.
with each other.
Okay. So the answer to that is yes, we will have logic that optimizes. So when we talk about cores, so the Windows support covers both client and server / cloud. So on the client side, we do deal with I'm going to call it big cores and little cores. So our queue logic does factor in those types of attributes in terms of making the decision of what cores to associate with which submission queues and completion queues.
Maybe this is more a client issue that we could easily extend to the server, which is the non-operative power states and all power state management. Is that being changed with this new multi-MQ thing, or is that handled separately?
So the question is, what is the support like for the non-operational power states that are defined in NVMe? So So within Windows itself, on Windows client, we have a OS-based power management system where we are using the non-operational power states of an NVMe device. So that same design will carry over from our current SCSI-based stack to the new StoreMQ stack, and that is already implemented and available in the preview builds.
So in your the stack diagram, the NVMe equivalent disk, I saw that out of the bottom of that was coming here, MJ read or MJ write. So to me, in my mind, and I wasn't told, but that's what's coming in. So what does that component do?
So the question is in the stack diagram that I shown earlier. As part of the StoreMQ stack, we have a new disk level driver called NVMe disk. So the functionality of that driver is very minimal. There are IOCTOs that are supported today at that layer that we have to continue to support going forward. But overall, the functionality that's performed at the disk layer, we vastly reduced that.
There's no transformation on that.
No, there is no. Right. So the question was, are there any transformations being done in NVMe disk? And the answer is no.
On the current store port, you have a back-off logic.
Yeah.
For starting the queue, most likely you don't need that back-off, or you still.
Okay, so the question is, in the current store port model, we have some back-off logic to deal with cases where we maximize all of the hardware capability, we still have requests coming down. So in this new StoreMQ stack, we still have some similar logic to deal with that situation. Because at the hardware level, there are limits to how many requests that you can send to the hardware. And when we reach that limit, we have to still be able to deal with incoming requests. So we will have support to deal with that situation where if the hardware capabilities are overwhelmed and being in use, we will queue those requests, and as resources become available, submit them.
But let's say the number of requests would be much higher because I think it's 254 today on the smart board for like LAN devices.
Okay, so okay.
Stack, like if you were using NVMe devices on the current starport, most likely see more backups because of the logic itself, rather than the device being overwhelmed in the case of an NVMe device.
Okay, so the question is with the current SCSI-based model, we do have defaults for the number of outstanding commands that could go to like a logical unit or adapter, and the default, but we also have APIs for a miniport to adjust this also. So the default that's used is only used if the miniport doesn't override them. So.
But today, most vendors do not implement that in their miniport, at least for disk.
Okay.
It's store NVMe. I adjust that.
Right. So for the Microsoft NVMe driver in the current SCSI stack, the number of outstanding commands that you could issue to the device is very high. We pretty much say, if the device indicate I could support N, we'll let it all N go to the device.
Yeah, but since the start NVMe is below starport, and from an application perspective, we are being blocked at starport.
No. The store NVMe is using available short port API to adjust those outstanding command limits. So the 254 that you mentioned, that doesn't apply to the Microsoft NVMe driver. The Microsoft NVMe driver basically looks at what is your supported I/O queue depth, and then the number of I/O queues we've allocated, and we will allow the number of I/O queues times your queue depth outstanding to the device.
So I am glad that you're doing this. This is neat. I did have a question about the separation of the store port and the store MQ mini port layer. When you guys were putting in the separation there, were you thinking at all about multipath when NVMe does come along?
So the question is, as we work on designing store MQ, what does the multipathing support look like?
I know you don't have it now.
Yeah. So the multipathing support, we have not currently implemented it on our new store MQ stack, but we will be doing it there. And my expectation is the way we do multipathing in this new store MQ stack will be different than how we've done it in the past in our SCSI-based stack.
Scott, do you have an indication on the performance?
So the question is, do we have indications on the performance of what a store MQ mini port would have? So the numbers that I have are from the Microsoft NVMe driver, because we do have a version that can work in this new stack. We haven't been able to test with a lot of different configurations, but with the configurations that we have, which is using a small number of like Gen 5 devices, it could do like 3.3 million. I mean, overall, we see that for raw disk IOs, that we're seeing an improvement in terms of CPU efficiency about 40%. We could definitely hit whatever the device can support. If we were to use our legacy SCSI stack, we can't hit the device max performance from a random IOPS perspective. The question is around support of NVMe features. So as part of this effort, the thing that you should expect is whatever NVMe features that we support today in our legacy stack, it will carry over to our new store MQ stack. Now, in terms of new feature support, I think it's really going to be based upon, is there an end-to-end story associated with that feature? If there's no end-to-end story, then I'm not interested in adding support for it.
Would you care, back on performance, would you care to predict how well you'll do when you get devices that can do 25, 50, 100 miles?
Yeah, that's a very good question. I don't know the answer. So definitely, if you have a device that could do 10 million, 25, 100 million, I am interested in trying it out.
Let's go.
One more.
Okay.
So I'm not hearing that Microsoft has any interest in the project going on in the SCSI committee to do a SCSI to NVMe translation standard.
Okay, the question is, does Microsoft have interest in the SCSI to NVMe translation standard? Yeah, I wasn't aware that there was such an effort. I know that the current NVMe, the SCSI translation, I think that was done maybe about 10 years ago by NVMe. Yeah, that one's very old.
Scott, thank you.
Yep. Okay, thank you, everyone.